on vapor pressure. So suppose this is a binary system, so there will be two components, and the two components is A and B. Okay, so the new pressure, that is partial pressure of A, which is PA, that will be actually proportional to P naught A. So P naught A is basically vapor pressure of the component A when it is in pure state, that is, it is not in the solution state. When the A component is pure, then the corresponding vapor pressure is P naught A. So here the partial vapor pressure in the solution, that will be proportional to P naught A, and if we remove the proportionality sign and use equality sign, then there will be mole fraction. Okay, so mole fraction, that is mole fraction of A. So how to calculate mole fraction? Suppose number of moles of A is Na and number of moles of B is Nb. So the mole fraction of A will be Na divided by Na plus Nb. That is the number of moles of A with respect to the total number of moles. Similarly, if it is Xb, that is mole fraction of B, that will be equal to Nb divided by Na plus Nb. So in this way we can calculate mole fraction of A and B, and these two mole fraction, if we add, it will always be equal to 1. So if we know the value of Xa, by subtracting it from 1, we can easily get the value of Xb. So it is denoted by capital X and capital that is capital X, in the suffix there is A or B. So when it is a pure liquid, that means now that is A is pure, that means there is no B. So in that case, mole fraction of A, that will be 1, because now here all the moles are basically moles of A. Nb is 0, so obviously mole fraction is 1. So under that condition, Pa will be equal to Pa naught. Similarly, if you consider that the component B is pure, that is, there is no liquid A, so in that case it will be Pb equal to in that case it will be Pb equal to P naught B. But when it is solution, just we have seen this expression. Similarly, for B component also, it will be equal to mole fraction of B multiplied by the vapor pressure of component B when it is in pure state, that is P naught B. So just P naught A, it is the vapor pressure of component A in pure state. Similarly, P naught B is also the vapor pressure of component B in pure state. So here all the discussion that we are doing, that is for liquid in liquid. Okay, so Raoult's law can also be applied for a solution of liquid in liquid. Now we will combine Dalton's law of partial pressure, which is basically from gaseous state, that is the law from gaseous state chapter, and Raoult's law, that in the solution chapter, but we can combine these two. So how we can combine this? So suppose the vapor of a liquid, if this vapor is behaving as if it is an ideal gas. So according to the Dalton's law of partial pressure, we know that total pressure is basically the total, if we add all the partial pressure of all the components. Here we have two components, but suppose there is mixture of A, B, C, D, then it will be P total equal to PA plus PB plus PC and so on. So in this case it is a binary mixture, so that is why we have only two components. So partial pressure of A, partial pressure of B, if we add this, we will get the total pressure, which is PT. Now from Raoult's law, we have already seen that PA is equal to XA into P naught A. So we will put this value in place of PA and XB into P naught B, which we will put in the place of PB. Fine. Now if we, so this is one expression, that is PT equal to this. We can also write XB in this way, so that in the whole expression there is no mole fraction of B. Or we can also write in place of XA 1 minus XB. Then in the expression there will be no mole fraction of A, it will be only mole fraction of B. So in this way, in different way we can write this equation, but this is as if combining the Dalton's law, which is basically partial, that is total pressure PT, that will be equal to partial pressure of all the components. Now in place of PA we are putting this expression, in place of PB we are putting this expression. So finally we are getting this type of expression. So total vapor pressure over the solution. In this way we can relate to mole fraction of any one component. So any one component, here we have chosen A, but we can also do it similarly for B. Okay, so only one component means either A or B. So total vapor pressure, that is PT, over the solution, that will vary linearly with the mole fraction of component A, because here we have kept only the mole fraction of A, not the mole fraction of B. Okay, so that is why the total pressure that will vary linearly with the mole fraction of A. But if we are keeping it here mole fraction of B, then it will be varying linearly with the mole fraction of component B. Vapor pressure composition curve. So what do we mean by composition? Composition is nothing but mole fraction. So this is basically mole fraction. Okay, so if we are saying that in a mixture the component A is present in 1 mole and B is present 4 moles, that means total number of moles 1 plus 4, that is 5, and out of 5 only 1 mole is A. So mole fraction will be 1 by 5. So in this way we can, when mole fraction is mentioned, that means we know the composition of the diagram. So suppose we have an ideal mixture of two liquids, that is A and B. Each of A and B. Now here ideal mixture, this term is important because we will also see what is non-ideal mixture. Okay, because some solution may act as ideal solution, some solution may act as non-ideal solution. We'll come to that later, that is non-ideal solution. But remember the discussion that we are doing now, that is for ideal mixture. Okay, so here we have ideal mixture of A and B, binary system. Each of A and B is making its own contribution to the overall vapor pressure of the mixture. Overall vapor pressure means total vapor pressure, PT. So here in the x-axis we have mole fraction. Now if we look at the left hand side, here we have 0 A and 1 B. That means at this point there is no component A, only component B, and in the right extreme we have only component A and 0 B. Okay, so if I am choosing any point, suppose somewhere here, so it will mean that 50% A or 50% B is present, but these are the two extreme. Okay, now in the y-axis, as if there are two y-axis, left hand side, right hand side. So in the left hand side we have taken vapor pressure of pure B, because here in this point we have only B because it is 1. Similarly at this point this is a vapor pressure of pure A. Now if you are thinking that why vapor pressure of B is high and vapor pressure of A is low compared to B, now this is completely arbitrary. You can also choose as if vapor pressure of pure A is high compared to vapor pressure of B. That is not important, but the important thing is here we have taken two components and their vapor pressure is different when they are in liquids, they are in pure state. So when vapor pressure that is only A is present, that is mole fraction 1. So this is the corresponding vapor pressure. That means it is basically PA naught and this is basically PB naught. Okay. Now as here vapor pressure of B is high compared to vapor pressure of A. So from this we can easily understand from common sense that here vapor pressure of pure A is less, that means its boiling point that will be very low. That is why the amount of vapor, because actually it is liquid, and if the boiling point is low, that means it will not remain in the vapor phase very easily. That means vapor pressure will be low. So from the vapor pressure, if two component their vapor pressure is mentioned, you can easily compare their boiling point. So if you know which one is more volatile, that means boiling point will be low and vapor pressure will be high. So here vapor pressure of pure B is higher than that of pure A. You can also take the opposite. It is just arbitrarily taken. So it also indicates that B is more volatile liquid, that means its boiling point will be low. So just from this information that which one is having more vapor pressure, you can easily predict which one will be more volatile. Higher the volatility, higher will be the vapor pressure. Next, what we will do, try to understand the difference between these two graphs. Now this is total, that is individual vapor pressure when they are in pure condition. But now when we are mixing it, that is except these two extreme point, if you consider any of this mole fraction, that means now it is mixture, it is not pure A and B. So when they are in mixture in different mole fraction, then what will be the corresponding total pressure? From Raoult's law we know that we have already seen that Pt equal to Pa plus Pb, and then in place of Pa we have written Xa into Pa naught. So from the equation we can understand how to calculate total pressure. But from graph, how we will correlate this equation with the graph that we are seeing here. So if we want to get the total vapor pressure of the mixture, what we have to do? We need to add the values of A and B together at each composition. So suppose if you are seeing this red line which is for A and the green line which is for B. So suppose we are somewhere here, so just draw a line. So under this mole fraction, this will be the vapor pressure of A, this will be the vapor pressure of B, and if we add these two, then we will get the corresponding total vapor pressure. Okay, so in this way all the points that we will get at different mole fraction, if we add all the points, we will get this blue line which is for total vapor pressure of mixture. And see here, this blue line is straight line, it is not curved line, it is straight line. And here if you look at the blue line only, you will see its maximum is starting at the pure vapor pressure of B and its lower point that is at pure vapor pressure of A. That means Pt, that is the total pressure, that will, its value will always remain between the vapor pressure of pure A and pure B, which is clear from the graph. Okay, so in this way from these two graphs we can get the total vapor pressure. Fine, and if we join all the line, we will get this type of straight line which is the blue line for total vapor pressure. Now composition of the vapor which is in equilibrium with the solution. So we have a solution, that is fine. So suppose in beaker we have a solution and here we have vapor. So in this vapor, what is the composition, that means what is the mole fraction of A or B? Okay, so the composition of the liquid and vapor that are in mutual equilibrium, it is not necessarily same. So here I have written that the mole fraction of vapor Xa Xb, actually it should not be written in this way, because mole fraction of A and B is basically the mole fraction of these two components in liquid state. So basically, see, now I am writing the arrow in this way, that means in the solution phase, this is the mole fraction which is denoted by X A X B. But in the vapor, what is the mole fraction? How to calculate that? That can also be calculated. And it is, remember, it is very important line that the composition of the liquid and vapor, that is the mole fraction ratio, it is not necessarily same. So the fraction Xa Xb, what will be in the liquid phase, and what the mole fraction ratio, what will be in the vapor phase, obviously these two will be different. Now it has to be different. Why? Because in the previous slide what we have seen that B is more volatile. So if B is more volatile, obviously in the vapor phase its mole fraction will be high, because it will prefer to remain in vapor phase as it is more volatile, that is low boiling point. So that is why in the vapor pressure now the mole fraction of B will be high. Okay, so from common sense we can understand that the vapor pressure should be richer in the more volatile component, which in this case we have arbitrarily chosen B, but not necessarily it has to be B, it may be for A also. Okay, So there are two mole fraction, one is in the liquid phase, one is in the vapor phase. So in the liquid phase, how to find out the mole fraction, that we have already seen, is Na by Na plus Nb, that is the number of moles of A and B. If you know in the liquid state, you can easily find out Xa and Xb. But what about the mole fraction in the vapor phase? That is the next thing. So in the vapor phase, if the mole fraction is Ya and Yb, we can find out Ya by applying this equation, that is Pa by Pt. So Pa we already know how to calculate. Pa is basically Pa naught into Xa. And in a similar way, you can also find out the mole fraction of B in the vapor state by taking this ratio. So Pb is basically Pb naught Xb. So if you know Pt, Pb naught and mole fraction, you can easily find out what will be the mole fraction of A and B in the vapor phase. Okay, so don't be confused between these two types of mole fraction, because when you will solve problem, you have to read the question carefully whether it is asking for mole fraction in the liquid state or in the vapor state. Okay, accordingly you have to use the formula. Raoult's law as a special case of Henry's law. So previously we have seen that how we can combine Raoult's law and Dalton's partial vapor pressure. Now we will see that Raoult's law is a special case of Henry's law. So in Henry's law we have seen that partial pressure in the mixture, that will be proportional to mole fraction of that component, and if you remove the proportionality sign, Kh is the constant, which is known as Henry's law constant. Okay, now what is Raoult's law? From Raoult's law we have seen Pi equal to mole fraction of I and the corresponding vapor pressure when the ith component, that is in the pure state. So you can find some similarity between these two equations. So if we compare the equations, what we will see, that the partial pressure of the volatile component or gas, that is directly proportional to mole fraction of the solution. So this is a common point. Fine. So what is the difference? Only here the difference is in the constant, that is Kh, which is called as Henry's law constant, and P1 naught, which is the pure vapor pressure when the component I, that is present in pure state. Okay, so in this way we can find some similarity between Raoult's law and Henry's law. So now we will solve a problem which is related to mole fraction and Raoult's law mainly. So here the problem is saying a solution has 1:4 mole fraction of pentane and hexane. So we have two components, both are liquid. Their mole fraction is given, that is mole ratio is given basically, not mole fraction. Vapor pressure of the pure hydrocarbons at a particular temperature, 440 mm Hg for the first component and 120 mm Hg for the second component. Okay, so that is pure, under pure condition, when what will be their vapor pressure, that is given. So we have to find out mole fraction of pentane in the vapor phase. So basically we have to now find, here the formula I have already written, we have to find Ya, that is the mole fraction of A in the vapor state, because in the liquid state what is the ratio of moles, that is already given. Fine. So 4 options are there. So first we will find out what is total pressure, that is Pt. So Pt will be equal to partial pressure of pentane, so I am writing here Pp, and partial pressure of hexane, that is after mixing the partial pressure. But in place of Pp, what we can write? P naught P into Xp, and in place of pH we can write P naught H and mole fraction of H. H means hexane. Now here mole ratio is given. So from the mole ratio we can easily find out what will be the Xp value and Xh value. So Xp is basically number of moles, suppose it is X, so total number of moles will be X plus 4X. You can simply also don't have, if you don't want to consider X, that is also fine. So it will be simply 1 by 1 plus 4. that means it is 1 by 5. Similarly for hexane, the mole fraction will be, now it is 4. So 4 by 1 plus 4, that means 4 by 5. Okay. So now we will write in place of P naught P 440 millimeter Hg multiplied by 1 by 5 plus pure the hexane, the corresponding vapor pressure is 120. This value, it will be multiplied by 4 by 5, the mole fraction of hexane, and this will be equal to 184 millimeter Hg. Okay. Now once we know PT, we can easily find out the mole fraction of pentane, because that is the final question we have to answer. So Y of P, that will be equal to P of P divided by PT. Now PT we already know, and PP is basically this one, because it is PP not XP. (1 by 5) divided by 184. Okay. So if we do the calculation, it will be 0.478. So this is a mole fraction, and mole fraction it has no unit. Fine. So correct option will be option C, 0.478. In the next problem, now we have a mixture containing 1 mole of volatile liquid A. The corresponding vapor pressure is given. That is, when it is in pure condition, what is the total what is the vapor pressure of liquid A, that is given, and 3 moles of volatile liquid B. That means in the previous question we have mole ratio 1:4, but now individual mole numbers are given. So basically the ratio is 1:3, and here the vapor pressure of B, that is also given. If solution behaves ideally, total vapor pressure of the distillate is. Now what is the meaning of this distillate? Distillate, this word is basically coming from distillation. So we will discuss in detail distillation after some time, but remember, when we do distillation, suppose we have a mixture of 2 liquids A plus B, we are heating this mixture. So when we are heating this mixture, there will be some generation of vapor, and in the vapor also there will be both A and B, but the ratio will not be same, because in the vapor phase obviously that component will be present in higher ratio which has higher vapor pressure. So in this case it will be A. So A will be now high compared to B. Now if this vapor, it is passed through some condenser, and then through this condenser, if it is collected in another container, so now the vapor, it is going through this column and it is collected here. Okay, so here temperature is low, so this vapor will again condense to some liquid, and in this liquid there is also A or B, or suppose only A, because it depends on the vapor pressure of A and B. But the point is, here we have to find the total vapor pressure of the distillate. So this is actually the distillate, that is the liquid you are obtaining by distillation process. This process is distillation, which is basically used to purify liquid compounds from the liquid mixture. So this distillate, what will be its vapor pressure, that we will find out. Okay. So obviously the meaning of this question is, it is asking total vapor pressure of the distillate, but actually it is asking the mole fraction in the vapor state. That we have to know, because if we do not know what is the mole fraction, we cannot find out the total vapor pressure in the distillate. Okay, so we again have to use this formula. So mole fraction of A, first we will find out. So PT, actually we can directly put it, because it is simply 1 divided by 1 plus 3. So PT will be equal to PA plus PB, that is equal to PA naught mole fraction of A, PB naught mole fraction of B. Now we will put the pure vapor pressure. which is 100, and mole fraction of A means 1 by 1 plus 3, basically 4, and PB naught 80 into 3 by 4. So after calculation it will be 85. Okay, so now we know the total pressure. So from this total pressure we can find out the value of YA and YB. So YA will be, that is, YA is basically mole fraction of A in the vapor phase. Mole fraction of A in vapor phase, and this will be equal to, from the formula we know it is PA by PT. PA is 25, PT is 85. So this will be 0.294. Now similarly, by following the equation YB equal to PB by T, you can find out YB, and another way also you can find YB, which is YB 1 minus YA, because if we add the mole fraction it will always be 1. So this value will be 1 minus 0.294, 706. So now we know what is YB and what is YA. Okay, now the total vapor pressure in the distillate. Total vapor pressure in the distillate, suppose it is PT prime, because total vapor pressure that we have already considered previously, so we cannot write PT, because PT and PT prime, these two are not same. This is the vapor pressure when it is here, but it is the vapor pressure of the liquid that we are getting after distillation, that is distillate. Now PT prime is basically equal to PA naught multiplied by YA. So try to understand the difference. Here PT is basically PA naught into XA, but here it is PA naught into YA and PB naught into YB. Now PA naught and PB naught both are already given. YA we have calculated 0.294, and this one is 80 into 0.706. So finally after calculation it will be 85.88 millimeter Hg. So it is matching with 85.88 is matching with option B. So correct option will be option B. Now we have already seen the curve of vapor pressure and composition. So in that graph there is vapor pressure in the y-axis, left hand side, right hand side, both side there is y-axis, and in x-axis there is composition, that is mole fraction. But now how we will correlate boiling point and vapor pressure. Okay, so if we know the vapor pressure composition curve, is it possible to draw from that curve what will be the corresponding boiling point composition curve? So VP composition curve we have seen, but what about BP and composition curve, that is boiling point composition curve? So if a liquid has high vapor pressure, that means at a particular temperature its molecules can easily escape from the surface, because high vapor pressure, it is very volatile. And if at the same temperature the second liquid, suppose second liquid is B, it has low vapor pressure, so in that case what will be what it means? It means that the molecules cannot escape so easily. So higher is the vapor pressure, the corresponding component can easily move from liquid to vapor phase. That is the main point. Okay. Now the question is, what does that imply about the boiling point of the two liquids? So now we know that if vapor pressure is high, it will be easily escaping from the surface of liquid to the vapor phase. But what does that mean actually regarding boiling point of the liquids? That is the question. So two types of explanation we can give. The first explanation is if the molecules are escaping easily from the surface, so it means that intermolecular forces are relatively weak. So that is why they can escape from liquid to vapor phase, because in liquid phase they are close to each other, the particles or molecules, whatever you say, they are close to each other, but in the vapor phase they are far from each other. So if intermolecular interactions are weak, then only they can easily move from condensed phase, that is liquid phase, to the vapor phase. Okay, and that means that we don't have to supply so much heat to break them completely and boil the liquid. That means they can easily escape to vapor phase. So we don't have to give much energy in the form of heat. Fine. That means boiling point will be low. So higher is the volatility. That means they can easily escape. Their boiling point is low. So this is one type of explanation you can give. Another explanation which is possible, either or. Liquid boil. When liquids boil? When their vapor pressure becomes equal to the external pressure, that is the external atmospheric pressure. Mostly it is 1 atmosphere. Okay. So not under all conditions the vapor pressure will become equal to the external pressure. So at particular temperature, when these two vapor pressures are equal, then only it can boil. Okay. So that is the boiling point. The temperature at which vapor pressure becomes equal to the external pressure. Now, if a liquid has high vapor pressure at a particular temperature, that means we don't have to increase the temperature very much until the vapor pressure reaches the external pressure. So our purpose is somehow we have to make the vapor pressure equal to the external pressure so that it can boil. But if it is already reached in high vapor pressure at some temperature, then we don't have to provide much temperature. On the other hand, what is the opposite case? If vapor pressure is low, then we have to heat it up. Now we have to provide energy a lot so that they can reach the external pressure. So now after providing heat, they are reaching external pressure. That means now it can boil. But for this boiling, we have to give more temperature. That is, more energy is required. So the main conclusion is that for two liquids at the same temperature, the one with the higher vapor pressure at a particular temperature is the one which is having lower boiling point. So these two are reverse. When vapor pressure is high, that is obviously if two components are given, if only single component is there, there is no question, because it is all the discussion is all about comparison. So we are comparing two components because it is a binary mixture. So how to compare? If one is having higher vapor pressure than the other, then it will have lower boiling point among these two components. Okay, so this is in this way. So this is the answer of this question. What does that imply about the boiling point of the two liquids? So this is the implication. Fine. Now we will see what is boiling point composition curve, because we have already seen vapor phase composition curve, and now we know what is the relationship of vapor pressure with boiling point. So now obviously we can draw the boiling point composition curve. So in boiling point composition curve, we will start from this diagram, because this diagram we have already seen in previous slide. We have vapor pressure in y-axis and also vapor pressure of pure A in other y-axis, and the green line that is for pure B and the red line that is for pure A. And if we combine these two lines, the corresponding total vapor pressure of the mixture line we are getting, which is the blue line. Okay. Now we are converting, that is, we are trying to make the boiling point composition curve. So now we have boiling point pure B in the y-axis, not vapor pressure, and boiling point of A in the other y-axis. Okay, x-axis is same just as before. Now see, boiling point of B is low, this height is low compared to boiling point of A, and it has to be because vapor pressure of pure A is low, so obviously its boiling point will be high. Okay, so now these two lines, if we join, we are getting a curved line. Now see, don't be confused between these two graphs. Look carefully. The first one is vapor pressure versus mole fraction. The second one is boiling point versus mole fraction. So here we are getting slightly curved nature of the graph. Okay, it is not necessary that it always has to be straight. There is no such thing. Now we have third graph. So what is so special about this graph? Now this blue line you have already seen in the second graph. Now in the third graph, suppose we are choosing some point here, composition of the liquid. So when you are here, basically now in the mixture amount of A is high because we are close to 1A, we are close to A point when pure A is present. Now what is the corresponding boiling point? This is the corresponding boiling point. So here the liquid boils at this temperature, that is why it is boiling point, because it is the boiling point curve, right? Now if you extend this line parallel with the x-axis, okay, we are reaching at a point which is giving us the vapor having composition at this point. Okay, so suppose this is point P, this is point Q. So at P point there is some particular mole fraction, we are hitting it, it is the boiling point, it is reaching the boiling point. Now if we move towards the left hand side, we are reaching another mole fraction. Okay, so why we are doing so? Because the new point that you are getting, this point is the vapor pressure of the that is this line, it will be the corresponding vapor pressure line. So see, in the fourth graph it is clear. Now this blue line, which is for the liquid, that is when A and B in liquid state, this is the line, but the purple line, that is for their corresponding vapor composition curve. So now we can say that suppose you are here at a particular point, amount of A is high compared to B. This is the corresponding line, corresponding point of boiling point. Now at this boiling point, if we consider the corresponding vapor phase, because we are keeping the temperature same, at this high we are keeping this height same. So at this height boiling point is fixed, temperature is fixed. So under the same condition, now you are moving to vapor phase. From liquid state you are moving to vapor state. Now notice the important thing here, the mole fraction, that is composition at this point, at P point, and composition at this Q point, obviously not same. That means under same temperature, if we consider the line at liquid over the liquid curve, and if we consider another point in the vapor curve, both are at the same temperature. Okay, so the corresponding mole fraction in case of liquid, where A amount is high compared to B, but in the corresponding line point which is in the vapor, now if you consider this point here, you will see it is close to 1B. That means now the amount of A is lesser than B. So what it means, that in vapor phase, when it is in under same temperature, amount of A will be decreased. So the ratio of A and B in the vapor phase and in the liquid phase are not same. Now this you can easily explain, because obviously the amount of B in the liquid, in the vapor phase will be high. Why? Because boiling point, that is amount of B is high. Okay, so why it is so? Because its boiling point is low. That means it can easily escape from liquid state to vapor state. So it is more volatile. So that is why in the vapor composition amount of B is high. But if you consider the corresponding point in the liquid line, now A is high. So in this way we can make the corresponding boiling point composition diagram starting from the vapor pressure composition diagram. Okay. So here no point on the curve must be higher than the boiling point of the pure A. So what is the meaning of it? This purple curve that we have drawn, if you look carefully, this is the maximum point and this is the minimum point. So here any point on the curve, if you consider, all the points are basically in between the boiling point of B and A. It is, if you consider any of this point, it is never higher than the boiling point of A, that is not in this region, there is no point. And also in the region that is below boiling point of pure B. So in this region also there is no point. So no point on the curve must be higher than the boiling temperature of the pure A. Okay. Obviously lower it will not be because it is already vapor phase. So the line will always be above the blue line. So that is why it is written simply that higher than the boiling temperature of pure A. So the points must not cross this line because this line is the boiling point of A. Fine. Now the important question, how we will use this phase diagram? What is the utility of this diagram? Why it is important? So here the same graph we have taken, but now we have some points. So suppose we are boiling a liquid mixture. Okay. So suppose this is composition C1. So at this point, at T1 it is boiling. So this composition, it has boiling point T1. Now under the same temperature, if we want to know the composition of the vapor over this boiling liquid, we have to draw a line to this purple so that the line can join this purple line. So this point, if you now draw a line to the x-axis, it will be C2. That means C2 is the composition of the vapor phase, and in C2 obviously the amount of B is higher compared to C1 situation. Fine. Now at C2, suppose what we are doing, if it is condensed, then it will reach at this point, right? And if you again draw a line, now look at the second graph. Now we are at point C2 again and a new temperature T2. So the liquid now will boil. When the liquid is at C2 composition, it will boil at temperature T2. It is not same as T1. T1 is different. Now T2 is here, which is lower than T1. Now again draw the corresponding, that is maintaining the same temperature. If you reach the boiling point, vapor composition curve, now see, if you look at the mole fraction composition, now it is C3. It is very close to B, 1B. That means gradually if you continue this process, that is C1, now you are reaching here, then this is a corresponding vapor composition. Now the liquid, if we condense, then again it will have composition C2, then again it is reaching to C3. That means if this process is continued, gradually what will happen, in the vapor composition there will be amount of B highest, and if you reach in at this point, then it will be totally pure B. And in the liquid phase, that is the distillate, remember in the problem that we have seen the picture of distillation, though we will discuss it in detail, but we know what is distillate. So in distillate there will be pure A, and in the vapor, sorry, in distillate there will be B, because B having lower boiling point, it is more volatile, so it will remain more in the vapor phase, so it will remain in distillate. Okay, that is after distillation, the liquid that we are getting, that is distillate. Okay, and the remaining liquid in the original container, that liquid will be reached with A, or you can also get pure A. So in this way, that is, if you follow this theory, you can separate the mixture of A and B, provided the their composition in the vapor phase and in the liquid phase obviously different, because if they have same composition then we cannot separate them. So the condition for distillation, suppose there are two mixture of two components, their vapor composition and liquid composition must be different. At same temperature it must be different. Okay, so you can see at same temperature always the composition is different. Okay, so again see, we collected and condensed the vapor over the top of the boiling liquid. That is, suppose the vapor is here, you have collected it and condensed it. What we actually do in distillation apparatus. Okay, so now you are reboiling it. So now we are reboiling it at some temperature T2, which is given in the next graph. So when we are boiling it at T2, now it will have a new composition C2 and it will boil at temperature T2, and a new vapor that will be generated, that will have composition C3. Okay, so this is the theory of fractional distillation. So that we will see in this picture. So here in the container we have mixture A and B. We are providing temperature, so there will be generation of vapor. Now here why it is called fractional distillation, because there is some fraction, some glass beads are there, or sometimes there is some spikes of glass. So what is the purpose of this? Because if glass beads are present or spikes of glass from the surface like this, if it is present, that means the surface area will increase, and as the surface area increase, what is the benefit? The benefit is here the vapor that are reaching all this surface, the surface are comparatively at low temperature. If you compare with this zone and this zone, obviously at lower temperature. So when they are in contact with some surface, they can easily condense again. They will come in touch with the vapor here. They will again, so this process will be going on in cyclic order. Okay, so that is why it is fractionating column, and from the thermometer we can watch the temperature, and this is condenser. Okay, condenser. Here cold water, it is basically this is the inlet. Okay, and here outlet. So here water is removed. So obviously here comparatively temperature will be high, here temperature will be low, and finally the liquids, when they will be condensed, because here we are running water, so the liquids are collected here, which is distillate. Okay, so this is the arrangement of fractional distillation that is normally done in the laboratory. So the process of separation of one liquid from another liquid, that means binary mixture, having different boiling point. So A and B having different boiling point, by distillation, that is known as fractional distillation. Now this distillation is possible only when the vapor phase has composition which is different from that of boiling liquid mixture. Remember in the previous graph what we have seen here, at this point T2, or you can also consider T1, if you consider this point which is the boiling liquid point, and this is the point at vapor line, so both these have different composition, and composition, the difference is so high. Here the composition is C2, here C1. So in liquid state amount of A is high, in vapor state amount of B is high. So this condition must be fulfilled. That is written in this point, that the separation is possible only when the vapor phase has a composition which is not same as the boiling liquid composition, and if the vapor is richer in the more volatile component, obviously the vapor will be richer in more volatile component, so the liquid that will be left behind must be getting richer in the other one. So in our case we have assumed arbitrarily that B is having lower boiling point, that means B is more volatile, so B will be collected here in the distillate, and in the flux, original flux, the component which will be remaining, that is actually A. So must be getting richer in the other one, A. And if it is the opposite case, suppose now B is less volatile, A is more volatile, so obviously in the distillate there will be A, not B. Okay. Now we have to know ideal and non-ideal solution, because in the fractional distillation theory we know now that when we can do distillation. So the criteria is that the composition of vapor and the boiling liquid must be different. Okay. Now it is not necessary that this condition will always be fulfilled. So in some cases this condition may not be fulfilled. So in that case, what will be the new scenario? We will come into that, but before that we have to know what is ideal and non-ideal solution. Because ideal is basically up to this point, whatever discussion is done, that is all are ideal. But it is not necessary, it will always be ideal. So if it is non-ideal solution, then what will be the case that we are going to see. But before that we have to know what is non-ideal solution. Liquid-liquid solution can be classified into two categories. Now this category, it is on the basis of Raoult's law. So it is very simple, the solution which obeys Raoult's law at all composition of solute in solvent. So whatever is the composition, if it is not, it doesn't matter, but it is always obeying the Raoult's law at all temperature, at all composition, we will call that type of solution ideal solution. Now enthalpy of mixing of pure components to form the solution, that is Delitzsch mixing. When we are adding A to B or B to A, it will be always 0, it must be 0. And another condition is volume of mixing must be 0. So there Delitzsch mixing 0 means what? It means there will be no heat generation, that is no heat evolution should take place, and no heat absorption should take place. It is simply 0, because if it is heat absorption, it is plus value. If it is evolution, it is negative value, negative enthalpy. Okay, but it should be 0. That is the condition for ideal solution. And Delvey mixing, that is also 0. That means after addition there is no increase in volume, that is expansion, and also no decrease in volume, that is contraction. Fine. We have some examples here. N-hexane, N-pentane, heptane. Both are hydrocarbon, they are having similar kind of nature, right? Only difference is in the number of carbon. Then bromoethane, chloroethane, again similar type of molecule. Only difference is bromo and chlorine. These two atoms are different. They are present in these two compounds. And benzene, toluene, again same type of compound. Okay. So you will mostly see that ideal solutions examples, the two components that are present, they are mostly of similar type. Now, what is the explanation behind this ideal behavior at molecular level? So why they will behave in such a way, and when they will behave in such a way, how to know? For that we have to look at the molecular level. So when it is in pure condition, the intermolecular attractive interactions in A, it will be AA type. Obviously now no B near A or no A near B. And pure B, there will be BB interaction. Now when you are mixing A and B, you have binary solution. So there will be basically three types of interaction: AA, BB and AB. So this is a new kind of interaction that will also be present. Now if these intermolecular attractive forces between AA and BB, they are nearly equal to those of AB, that will lead to the formation of ideal solution. So what you are seeing, that AA or BB, this is almost equal to AB, because see, exactly equal, that is not possible, but if somehow it is nearly equal, then also it will behave as ideal solution. Okay. So if there is large difference between these two types of interaction, then it will not behave as ideal solution, because when interaction is different, there will be effect on the corresponding vapor pressure. But if before mixing and after mixing the interactions are almost similar kind interaction, then there will be del H mixing 0 and del B mixing 0. Okay, so that is why you have seen already in these examples, that is mixture of NHN, N-heptane, bromoethane, chloroethane, benzene, toluene. Obviously the interaction between two benzene molecule and two toluene molecule and the interaction between one benzene and one toluene, obviously it will be similar kind because the molecules are similar type. Okay, so this is the ideal behavior we can explain at molecular level. Now the solution which do not obey Raoult's law over entire range of composition deviate from ideal behavior. We will call them non-ideal solution. So in non-ideal solution, obviously Pa not equal to mole fraction of A and P not A, because if it follows Raoult's law it will be equal, but now we will use unequal sign. So they do not obey Raoult's law. And now the enthalpy of mixing of pure components to form the solution and also the volume of mixing, they are not zero. Okay. Now if vapor pressure is high, that is before mixing and after mixing, if there is difference in vapor pressure and if the vapor pressure is high, because when we are saying that there is difference in vapor pressure before mixing and after mixing, there may be two options. One is either the new vapor pressure which is higher than the older vapor pressure. Another possibility is the newly generated vapor pressure that will be lesser than the original vapor pressure. So depending on these two cases, there is deviation, that is deviation from ideal behavior, and this may be of two types. The vapor pressure is higher, that is after mixing, when the vapor pressure is higher, then the solution exhibit positive deviation, and if the new vapor pressure generated is lower, it will exhibit negative deviation from Raoult's law. So these two types of deviation, what is the difference? That should be very clear. Fine. Now we will try to understand the non-ideal behavior at the molecular level, just we have seen in case of ideal behavior. So in case of positive deviation from Raoult's law, AB interactions are weaker than those of AA and BB. So in the previous case we have seen that these two types of interaction before and after must be same, but now they are not same. Now two things can be there, two possibilities. One is the new and interaction which is AB, that will be greater than AA or BB. Sorry, it is weaker. The first case is weaker. So if it is weaker, that means before it was higher, now it is weaker. So that is why there will be positive deviation. Why? Because as the new interaction it is weaker, that means they cannot move, they can easily move to vapor phase, because the interaction between A and B, it is very weak compared to previous situation, because here the interaction is very strong, but here the interaction is very weak. So weak interaction means what? They can easily escape from the condensed phase, that is liquid phase, to vapor phase, and that is positive deviation. And if it is negative deviation, now the interaction AB, that will be greater than AA or BB. So if this is the case, now we will say that it is negative deviation from Raoult's law. So the newly generated interaction, now it is very strong. So as it is very strong, that means they will not try to move towards vapor phase from liquid state. They will try to remain close to each other, because now the interaction is high. It is having more strength than before. So that is why now in the vapor phase they will have less tendency to move, and there is negative deviation from Raoult's law. Okay. So deviation from Raoult's law, here we have some examples of positive deviation, and you can also see the graph, that is the vapor pressure versus mole fraction. So y-axis we have vapor pressure. So this is x1, that is, suppose we have two components 1 and 2. So here x2 is pure, here x1 is pure, and all these points if you consider, this is mole fraction, and here the dotted line, that is actually for ideal case. So if it is ideal, it will always be following this straight line, but as it is non-ideal, So that is why ultimately the vapor pressure curve, that is the total vapor pressure that we are getting, that is deviating from the straight line. So as it is deviating from the straight line, we are calling it positive deviation. Okay, and these are the examples. Now you can see all the molecules, they are having different nature. It is not like N-heptane or N-hexane, toluene, benzene. And both side P2 is the pure, that is vapor pressure of two component when it is pure condition, and pure is the vapor pressure of X1 when it is in pure condition. Okay, and the examples of solution showing negative deviation, here we have some examples. And vapor pressure of solution, that is the P total, if you consider, this is a straight line, that is actual line that we can expect if it is ideal, but now it is lower. Now the vapor pressure is lower compared to ideal case, so that is why we are calling it negative deviation. So here vapor pressure must be lower, because now the newly generated interaction between 1 and 2, because now the components are 1 and 2 here we have considered, that is greater than between 1 and 1 or between 2 and 2. So that we have already seen in the previous, that is this last thing that I have written, AB interaction is greater than AA or AB. So here this is the same, only difference is now instead of AB we have taken 1, 2. So one interaction among 1 and 2 is very high. Before mixing there is no interaction between 1 and 2 because they are not close to each other, they are separate. But now they are close to each other, their interaction is high, they will try to remain in the liquid state, not in the vapor state. So that is why there is negative deviation. So I hope it is clear what is the difference between positive deviation and negative deviation.